In this presentation I will continue the discussion of Prony's method to estimate the mode parameters, and I will use a digital filter synthesis approach. We will meet a number of key concepts as usual: digital filter, filter coefficients, the filter's impulse response, the set transform, and the residual, that is the approximation error. So we know now from an earlier presentation that we can view our linear mechanical system as a filter, that when excitation sequence is applied, the filter responds with an output sequence X. So in the set transform domain, we can obtain the set transform of the response as the product of the transfer function of the system with the input sequence, the excitation sequence set transform. So obviously H, the transfer function here, can be viewed as a linear time invariant digital filter that transfers the input sequence, the excitation sequence, to the output sequence. So our problem can be formulated as a digital filter synthesis problem. So we have to find filter coefficients AN and BN, the denominator coefficients and the numerator coefficients, such that when we feed the filter with the exciting force sequence, it will respond with an output sequence Xn that as closely as possible fits or approximates our measured output sequence. So that is our task. So as close as possible, that means that we have to reduce the filter approximation error to a minimum. And that is, to do this, we introduce the residual, which is the difference between the measured frequency response function and our model frequency response function. So, but the problem with this definition here of the residual is that it is a non-linear problem in the AN coefficients, in the denominator coefficients. And that will cause some problems when we want to optimize the values of these. So instead we replace this residual with a modified residual. And to do this we multiply the original residual with the filter denominator. And the result then is this. We have here a linear expression in the numerator coefficients, and here we have a linear expression in the denominator coefficients. So this will be a linear problem, and that is very nice because that will simplify the determination of the coefficients a lot. So next thing we want to make use of when we continue the derivation of Prony's method is that we note that the frequency response function is actually the Z transform of the impulse response function. That is, the measured frequency response function is actually coupled to the impulse response sequence in this way, via the Z transform. So that means that we can replace the measured frequency response function with the Z transform of the impulse response function, the filter's impulse response function. So if we simplify this, we can express it like this. So here we have introduced a sum over the b and the denominator coefficients, and we have also simplified this expression. We have performed this multiplication, and if we now use the shift operator that we introduced in an earlier presentation and merge these two sums, and also note that the bn coefficients are 0 for n larger than q, then we can write this in the following way. So the terms here with z minus p times the impulse response function is actually then, from the shift operator, we know that it's equivalent then to time-shifted impulse response, like this. So we can now formulate the residual in this way. It's a sum of terms with z raised to the power of minus n. And we want now to make this residual, or the approximation error, as small as possible. So we set the residual equal to 0. And that means that each term in this sum can be identified to be 0. So for n equal to 0, that is when n here is 0, then we have this term, b0, and the measured impulse response function for the first sample for n equals 0 is also available. But this, the impulse response function for minus 1, that is 0, because the impulse response function is 0 for times smaller than 0, because we have a causal system. So all the remaining terms here are 0. So for n equals 0, we only have these two contributions. This. So this must be 0, if the residual should be 0. For n equal 1, then we get one additional term. We get b1, the measured impulse response function that's sampled at time 1, and also this term, sampled at time 0. But the remaining terms are 0. So then we get this equation. And then when n is increased further, we get an increasing number of terms in this equation. So for n equals to q plus 1, we get this expression. And note here now that since n now is larger than q, then bn is 0. So we have nothing here. We have 0 here. And this is the remaining equation. And then we can continue as far as we want. So this now, the equations for n larger than q will give us m linear equations for an coefficients. And if we use these to determine the an coefficients, we can use the q first equations to determine the b coefficients. So, to summarize, the mission we have is to determine the digital filter coefficients. We want to synthesize a digital filter so that it matches the measured impulse response sequence. And to do this, or rather when we have done this, we can determine our system poles and mode shape vectors that we need to do in order to determine our modal model of our vibrating system. So step 1 now is to use our measured frequency response function and inverse transform it to a measured impulse response function. So what we will get after this step is an impulse response sequence, Jn. Next step is to formulate and solve the linear system equations for our Am coefficients, where we now have m from 1 up to p. So we formulate the equations and solve for the coefficients. So in matrix form, we have a system matrix with known measured impulse response functions here, known impulse response sequences, and the right-hand side vector is also known from the measured impulse response function. So the unknown coefficient vector is here, and it's simply a linear system of equations. And you can also note that the system matrix, you see that it has the same element on each diagonal here, and that is characteristic for a tuplets matrix. Step 3. When we know the filter denominator coefficients an, we can determine the nominator coefficients bn by using these relations. And when we have done that, we have a set of linear equations for the filter coefficients of a digital filter with impulse response that we know matches our measured frequency response function. So mission completed so far. What remains now is to solve these equations and calculate the mode parameters from the filter parameters. And that will be the theme of the next presentation.